We're very happy to have as our next speaker, Jaewon, who's going to tell us about the universal spectrum of 4D SCFTs and holography.
All right, thank you very much. I'd like to first thank the organizers for organizing this wonderful conference. I'm very happy to be here and looking forward to other people's talk and interacting with you guys. So today I'm going to talk about some work that I've done in the past few years in collaboration with Sunjin Choi, Seungyu Kim, Junho Kim, and Seok Kim. Okay, there are so many Kims still, just like any Korean's papers. So, okay, I'm going to talk about something related to 4D superconformal field theories and its holographic dual, putatively. So to begin with, let me start with this basic question. When is conformal field theory holographic? What do I mean by that? So as you all know, the ADS-CFT correspondence asserts that conformal field theory in D dimensions is equivalent to a quantum gravity in one higher dimensional anti-de Sitter space. And what is emphasized in, for example, in this Magu review paper is that it is an exact equivalence between a non-gravitational and a gravitational quantum system. So since we have a better understanding of conformal field theory than quantum gravity usually, people like to call that CFT can be thought of as a definition of quantum gravity in ADS. So the strongest version of ADS-CFT correspondence actually asserts that if you are given any conformal field theory in D dimensions, that has to describe some quantum gravity in ADS-D plus 1. Of course, this is not a terribly useful statement because we don't really know what this putative quantum gravity theory is if you're given some generic CFT. Usually ADS-CFT, the most well-known examples of ADS-CFTs are all derived from string theory by taking some near-horizon limit of brains probing some Calabi-Yau singularities and so on. And my question here is that if I'm given some conformal field theory, then can we devise a diagnostic to test whether a given CFT is dual to a good-looking, weakly coupled Einstein gravity? So sometimes these are referred to as a holographic CFT in the literature. So this goal is partially achieved in two-dimensional conformal field theory, or ADS-3 CFT2, where you have strong constraints coming from modular invariance. And one of the famous facts that you can get from modular invariance is the celebrated Cardy's formula, which gives universal spectrum of high energy. So for example, what Cardy computed is that if you compute partition function at high temperature, then it is completely, it has completely universal form, which is controlled by this Virasoro central charge C. And if you take the Laplace transform of this, you get entropy of the states with some fixed energy, and that is also governed by central charge C and the scaling dimension. And one thing to notice here is that this formula is valid for arbitrary C. So it is actually valid for small c, but this formula is valid when your energy is high, very high compared to the central charge. Now, in vivo holography, we would like to take large central charge limit. So what we really wish to consider is a large central charge CFT. And what was shown in this beautiful paper by Hartman, Keller, and Stoica is that if you assume that a large CFT has a sparse light spectrum, I mean sparse in some suitable sense, then the partition function takes a universal form given in this fashion, which is actually identical to the Cardy's formula for a large temperature. And also the entropy formula takes the same form. But here the difference is that now C is very large, and this delta this is valid up to order C. And you can see that there's a phase transition of this partition function, and this formula accounts for the black hole entropy in ADS-3. So for any holographic CFT, we expect Hawking phase transition. So this is one universal fact about ADS gravity, that there's two competing phases. At low temperature, it is governed by thermal ADS, and at large temperature, the large black hole emerges, and there's a phase transition. And what Hartman-Keller-Sturka showed is that if you have a sparse light spectrum for a large CFT, if you apply modular invariance, it guarantees that Hawking phase transition has to exist. So something like that has to exist at the level of CFT partition function. So in this particular case, the Cartesian formula originally is supposed to hold for large energy for a small central charge. That becomes valid all the way up to like black hole threshold of low energy. Well, not low energy, but like to large enough energy. So therefore, you kind of see that the black hole is kind of emerged in this picture. If you consider a sparse light spectrum, then it guarantees black hole to emerge. Now, if you consider the same problem in the context of superconformal theory, then you can now study what's called elliptic genus. And what these people have shown is that if you do similar analysis of demanding Hawking phase transition of the elliptic genus, then it gives rise to a certain bound on the polar form, so-called polar form of the elliptic genus. So these are all very beautiful results in the context of ADS3 CFT2. And my goal today is to say something about higher dimensions. So to this end, I'd like to study 4D superconformal index, which is the direct analog of elliptic genus in 2D superconformal field theory. So you can consider an analog of Cartesian formula in 4D superconformal index that has been studied by this beautiful paper by DiPietro and Komorgowski in 2014. What they have shown is that if you study superconformal index at quote-unquote high temperature limit, more precisely it's about chemical potential, not really the temperature, then it takes a universal form that is governed by this difference between two central charges A and C. This is beautiful, but however, this is not what we want because it cannot account for the black hole entropy in ADS. So one of the motivating questions for a supersymmetric index back in around 2005 is that there was a discovery of supersymmetric BPS black holes due to Gutowski and Real. And one of the motivations is to use this supersymmetric index to account for the BPS black hole entropy. And unfortunately, that didn't work, namely due to this phenomena. There's a huge cancellation. So for a holographic theories, C and A are the same, so this vanishes. So it seems there's no degrees of freedom accounted by supersymmetric index. But recently, people realized that if you consider a suitable modification, namely it has to do with complexifying the chemical potentials, then actually the index is better behaved. So here I have replaced -1 to the f to e to the pi ir. And this still behaves like an index because it doesn't change the property of pairwise cancellation required by the index. So this seemingly just mild modification actually gives you a rather interesting modification to the Cardi-like behavior. And this is what we get. So instead of A minus C, we get this funny combination that does not vanish as we take A equals C limit or the large N limit. And what's cool about that formula is that it actually get us the black hole entropy. Once you take the Legendre transformation of this, would be the free energy. So you're using this index as an analog of partition function. Once you take the log of that and take the inverse Laplace transform, then you get the desired entropy formula for the BPS black holes. So that's great. So to recap, the superconformal index of 40n equals 1 CFT has this universal property at high energy, just like Cardi's formula in 2D CFT, which is controlled by the two central charges A and C. And if you take the Laplace transform, then go to the microcanonical ensemble, then entropy for fixed angular momentum scales like this. So it is actually governed by this funny combination of 3c minus 2a. So there's a chance that it captures something at high energy. And indeed, this is responsible for computing the black hole entropy. Now, so this is just about Cardi-like limit, which is valid for arbitrary central charge A and C. So central charge can be small, but delta has to be very large compared to central charges. So now for a holographic CFT, we'd like to take large n limit or large central charge limit. And this formula, since that accounts for the black hole entropy, where black hole exists far beyond the Cardi limit, it should valid up to the black hole threshold. So it should hold up to this regime for large central charge. So we gotta do the analysis in the large n limit, strictly large n limit, but not taking this Cardi-like limit of vanishing chemical potentials like this. So that's what we are heading for now. So okay, this is going to be the technical slide. So if you write the superconform index for generic n equals 1 gauge theory, it takes the following form. So it's written by some contour integral over some complicated looking integrands, which comprises of what's called elliptic gamma function. And it's simple to write it up anyway. So the terms in the numerator comes from the matter multiplets, and the terms in the denominator comes from the vector multiplets, the gauge fields. And this elliptic gamma function, which is a building block for our index, has interesting SL3Z transformation property that is periodic it's doubly periodic in sigma and tau. And also, if you take the kind of S-like transformation, then gamma is transformed to a product of two gammas. So this is not like the usual modular invariance of SL2Z. It's just a transformation property of the elliptic gamma function. It doesn't really leave this gamma to be invariant. But anyway, it's a very interesting property. And that gives us some handle to deal with this problem. So I can use this SL3Z transformation to rewrite the integrand in this form, where this V sigma and V tau are the quote-unquote SL3Z transformed integrands. And there is a prefactor, this P plus, and if you collect these terms, then it takes the following form. And what's remarkable about this is that if I take the Cardi limit of taking sigma tau to 0, then this part is actually exactly the form that you get from this Cardi-like formula that I presented before. So the thing is that now this factor is independent of U, so I can factor that out. So now the remaining job is to evaluate the remaining integral. And that remaining integral indeed becomes trivial if you take the Cardi-like limit, so nothing to worry about. Then the real question is to evaluate that integral without taking the Cardi limit in an honest large n limit. So here is the answer. So what we have found is that this large n matrix model admits some funny-looking saddle point described by this uniform parallelogram distribution of eigenvalues. So maybe it's out of battery. Okay, I gotta use this. So you see that so at each point there lies this UIs. So there are order n of these, so distributed uniformly among this parallelogram. So this is kind of stupid looking saddle point, which is kind of unconventional in the matrix model. But if you take this as an ansatz, it turns out it gives you a vanishing, it satisfies the vanishing force condition for the potential. Especially, this saddle turns out to be valid as long as you pick the gauge group to be a classical gauge group form in or its products. And if you restrict the matter fields to be in the representations of adjoint by fundamental or tensor representations. So whenever these are satisfied, it becomes a good saddle. And our saddle, the point is that it crucially relies on the periodicity of the potential. I told you that elliptic gamma function has this doubly periodic property, and we had to rely on that. And that also has to be combined with this gauge holonomy taking this form. And this thing actually gets broken if you have a large number of fundamental fields, because the fundamental fields breaks the translational symmetry. It behaves like a source term in the potential. So that's not allowed. So for example, if I consider SQCD in the conformal window where the number of flavors should be of order n, then our saddle doesn't work. In addition to that, we have to make sure that the saddle that I showed you before doesn't actually include any of the dangers. It would be singularities and branch points and things like that. So that could be potentially a problem. And luckily, we could actually find a regime of chemical potentials that is free of those singularities. And the conditions look like this. And what's interesting about these conditions is that it's quite reminiscent of the stability condition for the Euclidean BPS black holes studied by these people. So these are the conditions for to prevent condensation of Euclidean D3 instantons, according to these people. And these conditions look quite similar, and we don't really understand why these conditions has to be the same as this. This is just, for us, this is just a technical condition for our saddle to work. So it's an open question. And now that gives us to the final punchline is that we have the universal behavior of the index, which is identical to that of the Cardius formula that I presented before. So it's either this or that. It can be rewritten in this way if you turn on all the chemical potential for the U1 symmetries. And we find that for a large class of n equals 1 gauge series, Cardian large n limits actually agree all the way up to the black hole threshold. So this satisfies the necessary condition for a holographic CFT. So we gotta have a black hole. So at least this index is consistent with the fact that there has to be a black hole in the bulk. And our ansatz indeed works for the most of the well-known holographic CFTs, such as Kluber gauge theories dual to ADS5 times S5 mod gamma, or some Sasaki-Einstein manifold. And there are some notable exceptions. I mentioned this SQC in the conformal window. That doesn't work. And also SCFTs that has some dense spectrum in some suitable sense doesn't work. For example, if you consider like AKAN or Argyros theory and take large n with k fixed, then this thing doesn't work. Then that is not really a good holographic theory. Another thing is that there's also self-dominant saddle in our matrix model problem that is labeled by this integer k. And this k equals 1 saddle is our saddle that is responsible for the BPS black hole entropy. And that k equals 1 saddle means there's only one parallelogram, and that breaks one form symmetry completely. So it's like describing the deconfining phase, where the one form symmetry is spontaneously broken. But there exists also this quote-unquote k-cut saddle, where we have like a k copies of the parallelogram. So this also solves the saddle point problem. In this saddle preserves zk subgroup of the one form center symmetry. So that looks like it's either partially deconfined or partially confined phase. I don't know what that actually means, but these saddles do exist, but they are non-perturbatively self-dominant. So it's like e to the s over k, so it's very, very small. So in the normal circumstances, we can ignore this. But there's a case where we can actually, where this subdominant setup becomes important. So here's, so for the remaining 5 minutes, let me give you one application of our computation. So switching gears, let me just remind you of something. So Malasena and Papadonimas Raju have proposed to consider these functions called spectral form factor to probe a version of information loss problem. So it is defined roughly as a partition function squared, the complexified partition function squared of this form. And you see that there's a t, so there's a time t. So whenever there's a discrete spectrum, then this function will heavily oscillate in time. But one immediate feature is that for when time, at very late time, then E equals E prime states will dominate this, the spectral form factor. So if we take the time average, then basically there's a cancellation of the phases, so you reach this value, and this thing should not vanish no matter what. So whenever you have a discrete spectrum, then this, the spectral form factor will not vanish at late time. And that gives rise to a version of information loss because you can compute the spectral form factor using ADS-CFT correspondence. So you can compute this thing in the ADS bulk. And there, the dominant contribution comes from black holes. And that gives you a contribution like this. And it actually decays forever. So there's apparent mismatch between the gravity computation and the field theory expectation, where things should behave something like this. So it should go down and should go up and reach some plateau. So this particular plot is from this famous paper where they computed spectral form factor for the SYK model. But anyway, so this gives rise to a version of information loss problem. And in recent years, there has been lots of development on this problem. If you consider low-dimensional gravity, especially the Jacob-Teitelbaum gravity, this ramp region is explained by so-called double cone geometry, or space-time wormhole, which was demonstrated in this beautiful paper by SSS. But it comes with another puzzle because in the definition of spectral form factor, it should actually factorize. It's just a ZZ bar. So therefore, it doesn't really make sense to have this connected diagram summed over in the path integral. So this is not really allowed configuration. So, but if you do that, then that doesn't explain this ramp. So, and you do get by directly quantizing this JK, the JT gravity. So the interpretation is that JT gravity is believed to be dual to an ensemble of one-dimensional quantum mechanics. It's not dual to a single copy of quantum system. So that is the interpretation of this. But then being like more, how to say, if you want to be more conservative and believe in the conventional ADS-CFT setup, then we should be able to account for this mismatch without referring to like space-time wormhole or ensemble average. So, so it'd be great to have explanation without referring to wormholes or ensemble average. So that motivated us to look into the supersymmetric index version of the spectral form factor. So I will be brief in view of time. But the main idea is to consider complexifying the chemical potential, just like complexify the inverse temperature beta, and use this tau as an analog of time. And we can evaluate this index using the large n saddle point that I introduced. And we are particularly using this microcanonical version of the supersymmetric form factor for our convenience. And we can compute that using the saddle point approximation successively. And by the way, we are heavily motivated by this very nice paper by Yiming Chen, where he computed spectral form factor for free Yang-Mills theory. So here's the result. It turns out that if you just include the k equals 1 saddle in the spectral form factor, it decays. So it decays at some finite time. So it goes to 0 here. But then at this point, around this point, the subdominant k greater than 1 saddle kicks in, and it keeps the spectral form factor finite at late time. So at early, quote unquote, early time, or a tau, this black hole saddle is the most dominant one, but it becomes subdominant at late time. Now, at late time, this k greater than 1 saddle dominates, and it saves us from the quote unquote information loss. And these subdominant saddles are due to quote unquote orbifolded Euclidean black holes. So here we kind of restore the information without referring to the space-time wormholes or ensemble averaging. So, okay, so that's all I wanted to say. So let me summarize. So superconformal index at high energy has a universal behavior that we refer to as a Cartier-like limit. And we found that a large class of large n-Suzy gauge theories have a universal saddles that accounts for black hole entropy and the Hawking-Page transition. So for those guys, this Cartier-like formula is valid all the way up to the black hole threshold. And this universal saddle also has the subdominant saddles labeled by the unbroken one-form symmetry. And we can use this to model an analog of an information loss problem. So there are some future directions. So far, I've been only considering Lagrangian gauge theories to find this quote-unquote universal saddle as a criterion for a theory to be holographic or to have some emergent black hole. So can we actually do this without referring to Lagrangian? And the Hawking-Page transition is just one of the requirements for the theory to be holographic. So we need actually more than that. So the question is, when can we actually do this? It's technically harder to generalize this thing in higher dimensions because, for example, in 3 dimensions, there are like monopole contribution to the supersymmetric index that makes it harder to analyze. But anyway, it'll be nice to study those. And this is more, finally, I have a rather speculative remark that somehow the BPS sector, we know that BPS sector cannot be chaotic, but this index version of the spectral form factor seems to show some interesting behavior. So that brings me a hope that maybe we can mimic some phenomena in quantum chaos even in the BPS sector, even though it's not really chaotic, but maybe there is some version of that. Okay, so that's the end of my talk, and thank you very much for your attention.